In 12.3 lessons, we're going to be talking about how to graph polynomial functions. And the very beginning will seem kind of basic to you, and we're going to start out by really just doing a t-chart. So if we take a look at the first one, f of x equals negative x to the fourth, we'll start out with the basic x and y t-chart, and we'll put some values in for x. And what we'll do is we'll start plugging these in. When I take negative 3 and I raise it to the fourth power, you're going to get 81, but then you're going to negate it, so you're going to get negative 81. When I put in negative 2, you'll get negative 16. Negative 1 will produce negative 1, and 0 will produce 0, and then we get negative 1, negative 16, and negative 81. And what we'll do is we'll just take this and sketch the graph. Now, obviously, if we're going by ones, there's not nearly enough room on this to get everything, but you kind of see what this looks like. So making a t-chart is one basic way we can kind of see some points of the graph. For number 2, you'll see that there are 4 different graphs: x to the cube, x to the fifth, x to the fourth, and finally x to the sixth. What I'd like you to do is either on your calculator or you can go to Desmos, and I'd like you to type each of these in individually and make the sketch of the graph here on the side, and make sure you clearly label which one is A, which one is B, and then down here which one is C and which one is D. So pause the video and take a few minutes to do that. So we'll start by taking just a quick look at y equals x cubed and y equals x to the fifth. The red line represents x cubed and the blue graph represents x to the fifth. And if you take a look right here, you can see they're very similar shapes. They both have a center right at 0, 0, or the origin, and they start low and go high. You can see, though, that the blue graph is slightly tighter to the y-axis. And as you reach the points, 1, 1 right here, you can kind of see them flip. Now, if we get rid of those and take a look at x to the fourth and x to the sixth, you'll see something very similar. The green is x to the fourth, and the purple is x to the sixth. Again, these two have very similar shapes to each other, almost looking like parabolas in a sense. And you can see that the purple hugs to the y a little bit closer up here. But then once you get to that 1 point, you can see that they kind of switch. But again, that origin's at 0, 0. I would like you again to pause the video, and for number 3, go to Desmos or your calculator and type these graphs in, and then go ahead and plot those on the graph. The first graph that you were asked to do was x to the fifth minus 2. And I just want to make sure that you're seeing the patterns for this. The blue line right here represents y equals x to the fifth. That's that one that we started with in number 2. And if you can take a look at here, do you see how the origin's at 0, 0? But the one that you just did in 3a has a minus 2 at the end. And you'll notice that, again, these are basically the same shape, except for the black line got shifted down 2 units, and that's because of this number right here, that minus 2. And we've talked about this several times this year about, patterns and graphs, and I just want to show you that these patterns are going to happen with these polynomials. So that minus 2 shows a vertical shift of down 2. In 3b, you were asked to graph the quantity x plus 1 raised to the 6th power. Again, what I have here is the purple one shows x to the 6th, something we did in question number 2, and that origin is right at the center. And what you were asked to graph that x plus 1, if you notice where the parentheses is and where that 1 is inside the parentheses, the graph shifted over to the left. So I'm going to get rid of that for a second, the red one. So there's the purple, the original parent graph. And here we have another one. So it's a horizontal shift to the left because it's opposite of the parentheses. Very similar to the phase shifts that we saw with all those trig functions and parabolas that we saw before. Now, before I show you part C, negative 2 times quantity x minus 1 cubed plus 3, I want you to take a look at the parent graph. This is the parent graph of x cubed. You can see the origin right at 0, and you can see the shape of it. Now, a few things are going to happen here. We have this minus 1. We have this plus 3. And think about what happens with that minus 1 and that plus 3, and then maybe even that negative 2 on the front. And a few things happened. You'll see the center dot right here. Well, actually, the center dot's right here. And what happened is it shifted to the right 1 unit, and it shifted up 3. So that center dot, if I can get on there, is 1, 3 compared to the origin of the other graph. What also happened is you'll see the reflection. This red part going up now is going down because it's a reflection on the x because of that negative right here. And let's get rid of that negative for a second. And you'll notice it's a little bit skinnier than the red one, so it's closer to the y-axis and hugs it a little bit more. So again, all those things of patterns of graphs that we've been doing, they're going to apply here. We got to make sure that we have a good understanding of how the vertical shift or horizontal shift happens, along with changes to A to make it skinnier or wider. One thing I also hope you picked up with when we were looking at the original graphs in number 2 is the exponent, the 4 and the 6 versus the 3 and the 5 right here. I'm going to get rid of the exponents of 4 and 6 for a second. And I want you to notice the directions of the odd ones. X to the third and x to the fifth. And if I add one more, x to the, let's say, ninth, it being odd, notice it has that same flow. Starts low and goes high. Versus our even exponents, which come up, go back down, but they come back up again. That has to do with the power or the degree of the polynomial. And there's a few things that you can kind of see. With an odd degree, they will go in different directions. So it might start low and then go high, or they'll go high and then go low if there's a negative in front of it. And if the degree has multiple or is higher than 3, there might be different curves. I'll come back to that later. But whereas with an even degree, notice that they're going in the same direction. So this is it's pointing up, and then this is pointing up. Or it could point down, but if it's an even degree, it's also pointing down. At this first graph right here, this is an example of a graph that has a degree of 3, meaning that the exponent would be 3. Now, this isn't exactly this one, but maybe it's something like x squared plus x. And because this highest number is 3, that states the degree. And you'll notice that it crosses the x-axis 3 times. If it crosses the x-axis 3 times, that means it has 3 real zeros or solutions. So there's 3 real answers for that. You can also take a look at the directions. Do you see how this goes 1, 2, 3? If it has a degree of 3, it's going to have at most 3 directions. It could have less, like we saw in the examples, but at most it's going to have 3. And then I want you to kind of take a look at this right here and this right here. Those are, we're going to come back to those a little bit, but those are called turning points. Now, if you look at this one right here, this also has a degree of 3. You can kind of see the directions, 1, 2, 3, but it only hits the x-axis once. that's going to tell you it's only going to have one real solution. Now, if it only has one real solution and has a degree of 3, that means that it would have 2 imaginary solutions. They should always total up to be the number of degree. And kind of what we talked about a little bit last section is that there should be an even amount of imaginary numbers because they should be conjugates to kind of cancel each other out to get real numbers. And finally, in this last graph, you can see it's a degree of 5. And you can see that this has a lot more terms to it. They still go opposite because the degree are odds. So one's going down, one's going up. You can see the turns. 1, 2, 3, 4, 5. Again, a degree of 5 doesn't have to have that many, but it will have at most 5. You can see with this one in particular that the graph only hits 3 times. But again, the degree was 5. So if there are 3 real, there needs to be 2 imaginary so that it has a total of 5 degrees. The same thing can be said for these even degrees. Do you notice how, though within even degrees, they're going to point in the same direction? And that has to do again with those turning points. If this is a degree of 4, there's 1, 2, 3, 4 turns to it, or 4 directions to it. And you're going to have 1, 2, 3 turning points. You can see in this case it crosses twice. So if the degree is 4 and it has 2 real solutions, it will have 2 imaginary. This one, it tells us is a degree of 6. 1, 2, 3, 4, 5, 6, if you followed the little dot. But it hits 4 times. So 4 real zeros or solutions and 2 imaginary solutions.